30 miles an hour, winds the size of a grown man's arms, and not one sound. Somewhere in the wall of black spruce that wars off a Canadian valley from the rest of the world, a deer mouse pauses, its whiskers twitch. Its ears, two impossibly sensitive dishes of cartilage, rotate independently, scanning the dark like radar. This mouse has survived foxes. It has survived weasels. It has memorized the sound signature of every predator that hunts this forest floor. But it has never heard what's coming for it right now, because there is nothing to hear. 30 feet above, a great horned owl folds its wings into a silent dive. A red-tailed hawk, crossing the same airspace, would announce itself with a percussive whomp wing beat slapping the air, a rhythm any prey animal could catch and calculate. The owl produces none of that, no whoosh, no flutter, nothing but 2 amber eyes and 11 feet per second of closing distance. This is not luck. This is not some vague evolutionary nicety. This is one of the most sophisticated pieces of biomechanical engineering in the animal kingdom, millions of years of aerodynamic refinement, built one feather at a time, to solve a problem that, on paper, should be physically impossible to solve. Because flight is loud. It has to be. Air displaced at speed creates turbulence, and turbulence creates noise. That's not an opinion, it's fluid dynamics, the same physics that makes a jet engine roar and a hummingbird hum. Every bird that has ever flown pays a tax to the sky in decibels, every bird except this one. Tonight, we're not just watching a hunt, we're dissecting a machine, a killing machine built from keratin and air, engineered by evolution to do something that should break the rules, and by the time we're done, you'll never look at silence the same way again. To understand how strange the owl's silence really is, you have to understand what flight is supposed to sound like. Watch a pigeon launch off a rooftop and you'll hear a sharp, clapping rhythm wingtips slicing air fast enough to create audible shock waves. Watch a red-tailed hawk drop from a telephone pole onto a rabbit, and even from 100 feet away, you'll catch the rush of displaced air, a sound like someone shaking out a heavy blanket. Birds are, by the basic rules of aerodynamics, loud machines. Their wings are essentially fast-moving paddles cutting through a fluid, and any paddle moving through any fluid generates noise as it goes. This is where scientists studying raptor acoustics first ran into something that didn't add up. Researchers recording the flight sounds of different owl species found that at frequencies above roughly 2 kHz squarely within the hearing range of small mammals, owls produce dramatically less acoustic energy than other birds of similar size and wing loading flying at comparable speeds. In practical terms, to a mouse's ears, a barn owl gliding overhead is close to acoustically invisible. That's the mystery scientists have spent decades trying to reverse engineer. Not just why is the owl quiet, but how does an animal bound by the same laws of fluid dynamics as every other bird manage to almost completely erase its own acoustic footprint? Because here's the uncomfortable truth about physics, it doesn't make exceptions. Air is air. A wing pushing through it at speed will always generate some noise. The owl hasn't broken the laws of aerodynamics. It has found a way to work within them so precisely, so surgically, that the noise gets suppressed before it ever fully forms. That solution starts at the very edge of the wing in a structure so small you'd need a microscope to appreciate it, and so effective that engineers are now trying to copy it for jet turbines and wind farms. Run your finger along the front edge of an owl's primary feather, and you'll feel something no other bird possesses, a row of tiny, comb-like teeth, almost invisible to the naked eye, lining the leading edge like the serration on a steak knife. These structures are called fimbriae, and they are the first line of defense in the owl's war against noise. Here's the problem they're solving. When a normal bird's wing cuts through air, that air doesn't slide off smoothly, it separates into large chaotic vortices, swirling pockets of turbulent air that roll off the trailing edge of the wing. Big vortices are unstable. Unstable air is loud air. That rolling, churning turbulence is exactly what generates the audible whoosh you hear when a pigeon or a crow takes flight. The comb-like fimbriae along the owl's wing break this process apart before it can build momentum. Instead of one large chaotic vortex forming and slamming into the air behind it, the serrated edge slices the airflow into dozens of smaller, more orderly microcurrents. Smaller currents dissipate more quietly. Instead of one loud crash of turbulence, The owl produces something closer to 1,000 nearly silent whispers of disturbed air, individually too faint to register, collectively invisible to a prey animal's ears. It's a strategy borrowed, strangely, from something you'd expect to find in an engineering lab rather than a forest. Acoustic researchers studying wind turbine blade design have specifically referenced owl wing serrations as a model for reducing turbine noise pollution, an entire field of biomimicry built on copying what this bird figured out through raw evolutionary pressure, one failed ambush and one successful. Kill at a time. But the leading edge is only step one, because breaking up the big, noisy vortices at the front of the wing means nothing if the air rushing off the back of the wing and the friction of feather against feather gives the game away instead. That's where the owl's second weapon comes in, and it might be even stranger than the first. If you could touch a barn owl's feathers, and very few people ever get that privilege, you'd notice immediately that they don't feel like feathers at all. They feel like velvet. Soft, dense, almost furred. This is not decoration, it's acoustic armor. Most birds' feathers have a hard, almost plastic-like surface, built for durability and waterproofing. Owl feathers trade some of that durability for something the owl needs far more: silence. The surface of an owl's flight feather is coated in a dense mat of tiny, hair-like filaments, a downy, velvet-textured layer that does two critical jobs at once. First, it absorbs high-frequency sound. Just as a recording studio lines its walls with soft textured foam to kill echo and background noise, the velvety texture of an owl's feather physically absorbs the high-frequency acoustic energy that would otherwise radiate outward as the bird flies. Sound waves that would normally bounce and travel simply get soaked up in that soft microstructure before they can reach a prey animal's ears. Second, and this is the detail most people never think about, that velvet layer eliminates friction noise between feathers. Think about the sound of someone shuffling through a stack of paper or fabric rustling against itself. Birds with stiff, hard-edged feathers make a similar sound every time overlapping feathers rub together during a wing beat. It's subtle, but at close range it's audible, and to a small mammal's hypersensitive ears, subtle might as well be a siren. The owl's velvet coating acts as a buffer between feathers, absorbing that friction before it becomes sound. The result is a bird that can beat its wings inches from a rodent's nest and produce essentially zero acoustic evidence that it was ever there. Layer this on top of the serrated leading edge and you start to see the full picture. This isn't one clever adaptation. It's a coordinated system: turbulence control at the front of the wing, sound absorption across the whole surface, each mechanism compensating for what the other can't fully solve on its own. But a silent wing is useless if the owl still has to fly fast and hard to stay airborne. Speed itself is a liability. And this is where the owl's entire body plan reveals just how far this evolutionary arms race has gone. Compare an owl's silhouette to a falcon's, and the difference is obvious even to an untrained eye. Falcons are built like missiles, narrow, dense, streamlined for speed. Owls look almost the opposite: broad, rounded wings that seem disproportionately large for the body they're attached to. That's not an accident of appearance. It's a deliberate trade-off, and it's central to the whole silent hunting strategy. Owls have an exceptionally high wing area to body mass ratio compared to other raptors of similar size. In practical terms, this means an owl needs far less airspeed to generate enough lift to stay airborne. A falcon has to move fast to stay up. An owl can drift, almost hover, at speeds so low it borders on stalling, and that low speed is exactly what keeps it quiet, because acoustic energy generated by a wing scales dramatically with velocity. Slower wings simply displace less air, less violently, producing dramatically less noise as a byproduct. Then there's the wing beat itself. Owls fly with slow, deliberate, deep wing beats rather than the fast, shallow flapping you'd see in a smaller bird working to maintain lift. Slower wing beats mean less abrupt air displacement, no sudden pressure wave punching out ahead of the bird as it approaches. Combine the huge wing surface with unhurried, controlled flapping, and the owl achieves something almost a natural, controlled, sustained flight at speeds and volumes that shouldn't be aerodynamically stable and yet are, because every other part of the system has been optimized to make this specific. Inefficiency work in the bird's favor. This is the part of the story that should genuinely unsettle you, because everything we've covered so far, the serrated feathers, The velvet coating, the oversized wings, the slow deliberate beats isn't there to make the owl a better flyer in general. It exists for one single purpose: to deprive something else of information it depends on to survive. Small mammals like mice, voles, and shrews don't primarily rely on eyesight to detect predators overhead. In low light, in dense undergrowth, in the pitch black of a forest floor at midnight, their survival hinges almost entirely on acoustic threat detection, the ability to hear a predator approaching in time to bolt. That's the evolutionary bargain every prey species in that ecosystem has made. Fast reflexes, hypersensitive hearing, and a nervous system wired to react to the faintest disturbance in the air. It's worked for millions of years against foxes, against hawks, against weasels, every predator that, in one way or another, makes noise when it hunts. And then the owl arrives, and the entire bargain collapses. Because the mouse's survival strategy isn't built to detect an ambush, it's built to detect sound. Remove the sound, and you haven't just made the predator sneakier, you've disabled the prey's defense mechanism at its root. There is no reflex for silence. There is no evolved response to a threat that produces zero acoustic data. The mouse's ears, tuned with extraordinary precision to catch the faintest rustle, are rendered completely, catastrophically irrelevant. This is the real horror hiding inside the biology, not the strike itself, but the moment just before it. The moment where a prey animal that has done everything right, that has survived 100 nights through vigilance and acoustic instinct, receives no warning at all, no rustle, no whoosh. No time to react, because there was never any data to react to in the first place. Every piece of this system, the Fimbria slicing turbulence into silence, the velvet feathers swallowing friction, the oversized wings trading speed for stealth, exists to manufacture that single moment of total sensory blackout. It is, without exaggeration, one of the most refined ambush technologies ever produced by natural selection. Not built through intention, but through relentless, brutal iteration. Every owl that flew a little too loud, caught a little less food, raised a little fewer chicks, while every owl that flew a fraction quieter than its rivals, fed a fraction better, survived a fraction longer, and passed that fractional advantage forward. Multiply that fraction across millions of generations, and you get a bird that hunts using something close to zero information. In a forest built entirely around the ability to hear danger coming, the owl has become danger that produces no sound at all. And that should make you think, just for a second, about how much of what we call safety for a mouse, or for any of us, depends entirely on information we assume we'll always get. The owl is proof that nature doesn't play fair. Sometimes, the most dangerous thing in the room isn't the one making the most noise. It's the one that figured out, over millions of years, exactly how to make none. If you want to keep going deeper into the hidden engineering of the natural world, the adaptations most people never even know exist, subscribe to WildLabX. This is where nature stops being pretty pictures and starts being the terrifying, brilliant machine it actually is.